Okay. Seconds ago, you heard me say that no one really uses this. And I'll tell you why. It's impossible for it to go down as you add new variables into your explanation. For example, grade is equal to beta hat sub 0 plus beta hat sub 1 times hours of study plus your residual, okay? So let's say that you estimated this equation and you got an R square of 0.5, all right? You've explained half of the total variation. And then you think, well, now wait a minute. And by the way, we're later going to say this is not a good idea to do this, but you shouldn't just keep messing with the equation after you've run it. But anyway, but then you're thinking, well, but you know, honestly, I probably should have put hours of sleep in there because for me, that when I go to an exam tired, I don't do as well, even though, you know, maybe you waited to the last minute to study. So you've stayed up all night, and so you're really tired. That's not as effective as somebody that studied the same number of hours as you, but got 8 hours of sleep the night before the test, right? So you think, I'm going to add another variable here. Plus beta hat sub 2 times, call it sleep. So now you rerun it, and you have this new estimate for beta hat sub 2, estimate for beta hat and beta hat sub 0. It's impossible for this to be worse than what you just did. All right? It's impossible for this to be worse than the one that's just black, because the total amount to be explained is still exactly the same as it was when you started. How much grades varied from the average is exactly the same. It doesn't change given that you put a new variable in here to explain it. You might be adding a new x, but you haven't added a new y. All right? So this doesn't change in the r squared. And you can't explain less with the black equation than you can with the black equation plus the blue equation. All right? You can't explain less. And likely as not, even if sleep isn't related to this, it's going to be some random correlation and your R squared is going to go up. And so the problem is that you can put in variables like somebody's height or weight, or the example they use in the book was their student campus mailbox number. It's going to raise the R squared. It can't lower it. It's going to raise it. All right? So that's not very good, because what it implies to you is, geez, I should put like 10,000 variables in there to explain this. That'll get a really good R squared, which, by the way, you shouldn't do anyway, but it's a temptation. So we don't use R squared. What we use is adjusted R squared. Adjusted for what? Now, this is the last thing I worked on in my notes yesterday. And I think I came up with a better way to explain this than I have at any other time in this course, which would be good. Wouldn't it be good if I didn't like go backwards or regress, if you will? We're going to adjust R squared for degrees of freedom. And I really wanted to come up with a good way to explain degrees of freedom to you that makes it intuitive. Because again, the point of this book, where am I? A practical guide. We want you to be able to use this. I took 4 classes in econometrics in grad school. I took we were on quarters, the 3-quarter series that if you were going to specialize in econometrics, you would take those classes. I didn't take the exam. There's a big exam to say you're qualified in that, but I did take the classes that would lead up to that. We never ran a single regression. All we did was matrix algebra and calculus over and over and over. And I want to make sure that you actually have practice doing what you do with regression analysis, because that's what you're going to do in a job. All right? In a job, they're not going to say, hey, will you prove that ordinary least squares is the best linear unbiased estimator? That's not going to happen. All right, so let's see here. We don't use R squared. We use adjusted R squared. And it's adjusted for what? For degrees of freedom. Some people call adjusted R squared R bar square. I hate that. All right, it's in the book. They use R bar squared. Why do I hate it? I don't know. Quit asking these questions. All right, so we're going to adjust R squared 4 degrees of freedom. And let's see, shall I just show you the equation first? And again, the computer is just going to calculate this for you, but we want to show you where it comes from. The adjusted R square, oh, that's right. Remember a minute ago, that part I said, I'm not going to show you that. I don't think, yeah, then I was trying to remember why I even had it in my notes because of this. All right. Okay, let me show you this. Actually, this will work out well. R squared was equal to the sum of what there is to be explained divided into the sum of how much you did explain. All right, so here's the percentage of the stuff that you did explain. Now notice, however, that that's the same thing as 1 minus what you didn't explain. Right? This is the ratio of what you didn't explain. This is the residual. This is what's left over. It's what you did not explain. So this is the ratio of what you didn't explain to what there was to be explained. And this is the ratio of what you did explain to what there was to be explained. So if this is 0.7, then what's this going to be? 0.3. It's what's left over. It's what you didn't explain. So 1 minus 0.3 is 0.7. So R squared can either be expressed as the ratio of what you did explain to what there was to be explained, or it can be 1 minus what you didn't explain divided by what there is to be explained. Why did I do that? Because the equation for adjusted R squared is actually using this. Right? It's actually using this. It doesn't have to, but it does. Adjusted R squared, a line over the top of it. Or sometimes you see it written like this. ADJ hyphen R squared. If I'm writing a paper and that's kind of complicated to do in the word processor, I usually just write this. Right? So either one. And I'm going to close the door because Melanie and Alex are being noisy. Yeah, okay. All right, so what is the, I'm going to give you the formula first. I'm going to explain the logic underlying it afterwards. Adjusted R squared is equal to 1 minus, just like it was before that. But now it's going to be divided by sum of y sub I minus y bar squared divided by n minus 1. All right. Notice the new things we've added in here. We've added this and this. And of course the division symbol. Let me explain first. Let's see, n is the number of observations in your study. If it's 100 kids, n's 100. If it's 20 kids, then n is 20. Now, what we're trying to figure out over here on the far right is what's called degrees of freedom. Which to me has always sounded like a reggae band of some sort. But anyway, degrees of freedom. And the n comes from the number of observations. The 1 comes from the mean of the observation, and the k comes from the number of explanatory variables. Don't worry about this yet. Don't worry about it yet. Right, so I'm just telling you where it came from, so if you look back over this video later, then you're like, okay, well, he did explain that, and it might make more sense. But right now, I understand that it would not necessarily. But let's just focus in on the k for a moment. All right? And then I'm going to back off and explain degrees of freedom more clearly in just a moment. But look at the K for just a minute. That's the number of explanatory variables in your regression analysis, right? So if I have 1, just the hours of study, then K is equal to 1. If I have hours of study and hours of sleep, then K is equal to 2, and on like that. Notice what's happening here. As K goes up, all right? So this expression, let me circle it in green. So that expression is getting larger, right? Because we're making the denominator smaller. The larger K is, the smaller the denominator is because it's a negative number. And so that makes this whole number together larger. You don't want the part you didn't explain to be larger, right? That's the problem. That when this goes up, it makes the part that you didn't explain bigger. And so what this technique here, what this adjusted R-square is doing is it punishes you every time you add a new variable. And basically, the explanatory power of the new variable needs to outweigh how much it was punished by making K a bigger number. Now, I quite honestly don't remember from grad school why the equation looks exactly like this, because it was 33, 34, 35 years ago. But nevertheless, you can see how it works. As the number of explanatory variables go up, how much you didn't explain gets larger, so therefore how much you did explain gets smaller. All right? So how much the new variable truly adds to the explanatory power must outweigh the impact of a larger K. All right, so that's the basic equation. The computer's just going to spit it out for you, all right? But we want you to know what's going on here. When you add a new variable and you're using R squared, it'll just keep going up. All right, it's going to vary from 0 to 1, and it'll just keep going up. It might stay 0, but it's almost certainly just going to go up. This one, the R squared could go down. In fact, the R squared could even be negative with this equation right here. All right. What's it really talking about, okay? What is the underlying logic here? And, yeah, I'm not going to tell you that. Okay, the degrees of freedom. Degrees of freedom. Because I'm sorry, let me make sure you understand this. That what we're doing by adding a new K, is reducing the degrees of freedom. N minus 1 and N minus K minus 1 are the degrees of freedom. And you want, obviously, clearly in the numerator, you want that to be as big as possible in what's circled in red. And the degrees of freedom are equal to the number of independent, how do I write this out here? Pieces of information of info that went into the estimate. Yeah. Okay, I'm going to kind of back into this because it takes a minute to think about it. Degrees of freedom are the number of independent pieces of information you have that went into whatever estimate you're making, all right? Let's say you're trying to estimate the impact of a football team's winning percentage on attendance. All right, so the impact of a football team's winning percentage on attendance. Effect of win percent on attendance, all right? So that's what you're trying to, here's your estimate. The independent pieces of information, remember N is equal to the number of observations. Would you rather have 2 seasons worth of data? For let's say the, oh good Lord, it's not called the Southwest Conference, it hadn't been called that in years, John. Big Ten? What the hell's wrong? SEC. All right. That you're looking at the SEC and seeing the impact of the winning percentage of the individual team on how many people come to the game. Would you rather have 2 seasons of information on that or 20 seasons? Clearly, you'd rather have 20 seasons. You'd rather have lots of data to be able to take into account various factors in terms of what affects attendance, and in particular here, whether or not the winning percentage does. So the number of seasons is the number of independent pieces of information, right? So degrees of freedom is the number of independent pieces of information you have that go into your estimate. So for example, if the estimate is regarding the effect of winning percentages on attendance, you'd rather have as many seasons as you can get, all right? 1 season in the SEC is not terrible. You're going to have, what, 12 teams? I can't remember how many are in there. But it'd be nice to have 20, wouldn't it? Then you can probably get a much more reliable estimate. So you generally want as many degrees of freedom as you can get in econometrics, right? Because then that makes your estimates much more reliable. It is like flipping a coin twice versus flipping a coin 200 times to determine whether or not it's fair. 200 is better, all right? 200 is going to give you a better sense. So that's degrees of freedom. Now, what does that have to do with K, all right? So I've explained so far really just in terms of N. Well, yeah, not only does N affect your degrees of freedom, the number of seasons you've got, but what also affects the degrees of freedom is how much you're asking that data to tell you, how much you're requesting of it, which is adding a new independent variable. Let me read what I wrote here, and then I'll explain it. Not only does less data lower the degrees of freedom, if you have fewer seasons, lower the degrees of freedom, but so does more independent variables, which is the deal between these two right here. When K goes up, it's going to potentially lower this unless the explanatory power offsets it. Clearly, we'd like more N. But also, the value of N starts getting chipped away when we start adding more Ks, more independent variables, more hours of study, hours of sleep, SAT score, whatever. So that's because you are asking the same number of independent pieces of information to give a more detailed estimate. Going back to the grade example, say you have 6 students and how long they studied, and you run that regression. Now you get their data on their incoming SAT scores, how much coffee they drank, and how well they slept, and add these independent variables to the regression. You're really asking a lot of the data. You need more degrees of freedom. You need to have things vary in order to be able to figure out the regression line. What if everybody in class made a 75? What if everyone in class made the average grade? That kind of sucks for the data, because now you've got, well, I'm trying to explain no variation whatsoever. I need some variance. And that variance can only be, and this will become more clear later, I hope, but the more you are asking that variance to explain in terms of the impact of individual independent variables, the harder it is for it to do so, just as if you had lowered the number of observations you had. I want this set of data on 20 students to be able to tell me the impact of the hours of study they did, of the hours of sleep they had, the impact of how much coffee they drank, and so on. In fact, actually, there's a point at which if you add too many independent variables, you simply can't do it anymore, all right? It's like, I can't figure that out. You're asking me to correlate this over here on the right with 10,000 things on the left with 10,000 things on the right. I can't do it. I need more data, all right? So, that's the end of that chapter, all right? Let's see. Chapter 3 is awful short, and then Chapter 4 is kind of boring, to be honest. But Chapter 5, I'm dying to get to Chapter 5. So, may the force be with you.